Chapter 15, the last one of A's level, software development. So what are we going to learn in this? Let's have a look. That's the learning objectives of this. Yeah. Show understanding of the purpose of a development life cycle. So when you develop software, you don't just go to the computer, start something and test it and then give it. But we have to do it as a project, a nice methodical way. So for software development, there is a life cycle. So you have to understand the purpose of a development of life cycle. Why do you want to have a cycle like that? And understand the need of different development life cycles. Why do you need different styles or methods depending on the program being developed? So for one program, one method, for another program, another method. Describe the principles, benefits, and drawbacks of each type of life cycle. So they are like waterfall, iterative, and rapid application development. Those are the three methods we are going to learn today. Show understanding of the analysis, design, coding, testing, and maintenance stages in the program development cycle. So these are the stages. First, the analysis, then you design. Analysis in the analysis stage, you study the problem. Then find a solution, design the solution, then code it, like make the program. Then only you make the program, test it, and then maintain. Maintenance of either correct it or improve it or adapt it to different situations. There are different kinds of maintenance. So all those things will be learning. Then use a structure chart to decompose a problem into subtasks. From the beginning, we talked about decomposing a problem, breaking down to sub-problems, so subtasks. Makes it so easy. Then how to use a structure chart to do that. Then use a structure chart to express the parameters passed between the various modules, procedures, and functions, which are part of the algorithm design. So when you design it, you can use a structure chart to show what are the parameters passed between modules, like the functions and the procedures that you have, the modules, between modules, what are being passed, the data. Describe the purpose of a structure chart. What's the purpose of a structure chart? Then construct one. Construct a structure chart for a given problem. Derive equivalent pseudocode from a structure chart. Look at a structure chart and then write pseudocode, the relevant ones. Show understanding of the purpose of state transition diagrams to document an algorithm. So yet another way, one is structure chart. Then there's another one called state transition diagram to document an algorithm. Show understanding of ways of exposing and avoiding faults in programs. There are faults in the program. So how are we going to expose them and to avoid them? Locate and identify the different types of errors. 3 types of errors: syntax errors, logic errors, and runtime errors. Correct identified errors. Show understanding of available testing methods: dry run, walkthrough, white box, black box, integration, alpha, beta, acceptance, stub. So many ways, methods, testing methods. Select appropriate data for a given testing method. You need data to test the program. Show understanding of the need for a test strategy and test plan and their likely contents. Test strategy. Like any other project, you should have a strategy, how you're going to do it, and then the test plan, a definite plan with test data and their contents. Choose appropriate test data for a test plan. Appropriate test data for a test plan. There are three, namely normal, abnormal, and extreme or boundary. So in this case, the normal one should be accepted, abnormal should be rejected, that is error data, erroneous data, and extreme or boundary. Right? They are if it is a student mark system, the 0 and 100, they are the boundaries or the extremes of the marks range. So 0 and 100 should be accepted. But if you take the outside boundary, like -1 or less than -1, or anything more than 100, not all, those are the abnormal ones. But if you just take the boundaries, -1 and 101, those should be rejected. So extreme and boundary, you have to be careful. You will learn during the chapter, but some are acceptable, some are rejected. So understanding of the need for continuing maintenance of a system and the differences between each type of maintenance. The types are corrective maintenance, adaptive maintenance, perfective maintenance. We will learn the meaning of these and then the differences. Analyze an existing program and make amendments to enhance functionality. So an existing program also can be corrected or improved, making amendments to enhance functionality, to improve the functionality. Stages in the program development lifecycle. You solve the problem by designing the solution using structured English, a flowchart, and or pseudocode. You then wrote the program code and tested it. However, when large software systems are required to solve big problems, the following stages, which are more formal, have to be followed. Small programs you can do just like this. You write your own, you start from the structured English, write your flowchart and pseudocode or just pseudocode. Then you code it, test it, and then that's it, done. But not for big projects. For them, you should have this life cycle, development life cycle going on properly. Otherwise, you're going to have experienced disaster. So in the analysis, the first step is investigate issues and the current system, if there is one. So is there a system at the moment? Yes. In that case, you will have to study the system and then find the problems. If it is not there, then study the current manual system and get the issues investigated. Also define the problem clearly and precisely. Draw up requirement specification, because this is going to be the most important document. Define the problem clearly and precisely. If not, you will not get the correct answer. Plan solution. So in the same stage, analysis stage itself, you have to plan the solution. Decide most appropriate solution. There may be more than one solution. In that case, decide on the most appropriate one. Most effective, most economical, not most economical, but you have to have a balance. Strike a balance between the two, the cost and the benefits. So decide how to solve problem. It is also in the same analysis stage. Like, is it going to be bottom up or top down? Bottom up is start with a small sub problem and build on it. Start a small one, small section, and then build on it. Otherwise, top down. From the top, you start from the very big problem. But then there is a tool called stepwise refinement. So going down, that is like the decomposition. You break this full thing down to pseudocode or flowcharts or structure charts. So that is, you're going to decide how you're going to solve the problem. Then comes the second stage, design. A thing called identifier table, you already know. The variable name or the identifier name. Then another column for description, the data type. The purpose, let's identify a table. So that this stage, you'll have to decide on that. What are the variables you're going to use? Not when you start the program. Starting to code is this here, coding, the third stage. But here itself, you have to identify what are the variables you're going to use, what are the constants, what are the procedures, all those things. Then data structures. At this design stage, you have to decide what are the data structures you're going to use. Is it 1D array? Is it 2D array, which are in the memory, main memory or RAM, or else files on the hard disk, permanent. You have to decide. Or design, rather, decide and design what type of array, what type of file. Then plan algorithms, flowcharts and pseudocode. So during the design stage, these are the things. We have to plan on the algorithms, the flowcharts and the pseudocode. Once these are ready, pseudocode is false code. It's not real code, it's false code. Pseudo meaning false. So now it's the stage or the time to put this into real code. The after the language is chosen, right? Coding, also called implementation, implementing this pseudocode. So choose high-level language. You have to choose the high-level language that best suits the problem, or language you are most familiar with, or both. You have to consider both these things, factors, when deciding what language you're going to use. If you select a language that you don't know, then it's a problem because you have to learn the language first. Then testing. After coding, imagine that the coding is finished now and the testing comes. So to ensure the program really works under all circumstances, test with all the possible data. You have to imagine, you have to visualize what the operator or the user will input. For the name, will the user input age? That kind of all way out things, conditions we'll have to think and test out what happens, whether it will be accepted or rejected. So that is the end of it, the cycle. And in a diagrammatic form, here it is, the program development life cycle, starting with the analysis, design, coding, testing, maintenance. While maintenance stage, you can get more problems, while you are using. Now you are using it, then ongoing thing. Also, you can get more problems. Then again, analysis, design, coding, go on. That's why it's a cycle. So let's learn the waterfall model first. This model is straightforward. When you look at the diagram, you will see first the analysis, then comes design, then coding, testing, maintenance. Easy to remember. This is just like this our normal cycle in step by step. You can't do the coding before this is done, or you can't do this before this is done. So that is why waterfall. First from there to here, from here to there, like that it goes. But of course, you might wonder, then what is this going up? But this is for software maintenance. You can, not like water. For water, you can't go up. But then for software development, you can, maintenance, then test again, maintenance, find errors, maintain, like that it goes. You can have a cycle here also. Coding, testing, errors, then correct it. Like that it goes on. The waterfall model. Then we come to the second method, the iterative model. Iterative. Benefits include the following. So straight away we are going into the benefits because there is no diagram like that, this for that. There is a working model of the system at a very early stage of development, which makes it easy to find functional or design flaws. So here, the main thing is, you have a working model of the system at a very early stage. When do you have a working model in this model? Is it there, here, there? No, only after this. At this stage, yes, coding, once you finish the coding, you have a working model. So maybe 3-4 months for this type, for this stage. So you have to wait. Whereas the iterative one, a working model. So that means you start something small first. without doing the whole system, just takes one small thing and then start a working model of the system at a very early stage of development, which makes it easier to find functional or design flaws. So when you design and then the functionality, you can check the design. Is it okay? Is it going? If we expand on this, will it be okay? Or no, this is wrong. We have to start again. So very early stage, you can find issues at an early stage of development means corrective measures can be taken more quickly. Otherwise, you have to wait in this model, you have to wait till this place, this stage to do any corrections, to find any errors. At this stage, you don't find any errors. At this stage, you don't find, not at this stage either. Then some working functionality can be developed quickly and early in the life cycle. So that's the same thing in a different way. Functionality can be developed early. Results are obtained early and periodically. So all these are due to this early working model. Parallel development can be planned. That is another one. You can take one part and then take another one going parallelly. Progress can be measured. Progress also can be measured, whereas here you can't. Until you come here, you can't do any progress of the system. Less costly to change the scope requirements. Now imagine you're building a house. If you saw that the kitchen is in the bedroom at the early stage, like when you lay the foundation and then the finish the foundation, you find the error there, some error in the plan or design, you can correct it, just remove only that part. But consider the case where you build up to the roof level. Just before putting the roof, they find the error. Then what you have to do? You have to break the whole thing, all the walls together with the foundation and then restart of that part. But here it is the very early stage you can check. Less costly to change the scope or requirements. At that stage, if you find that the kitchen should be somewhere else and also you can change at that point, even if your original plan was one, and still if you want to change, it's very less costly. Early stage. It's an early stage, it's less costly. Otherwise, you have to break down. Similarly, in the software also, if you have to redo from, you have to change and redo, there's a whole lot of work involved, more difficult than the physical building of a house. Physical building of a house, no, it's very easy. You can see it. This wall here, that wall. But in software, when you make a small change, you don't know how and where it will affect. There's a whole lot of things to consider, and it's very costly. Testing and debugging offers testing and debugging of a smaller subset of program is easy. So small subsets, subtasks or submodules is easy. Testing and debugging. Testing and debugging. Bug is the error in a program and debugging is correction of that bug. Risks are identified and resolved during iteration. So iteration, when you like loop and then find the risks and resolved. Identify them early and resolve them early. Easier to manage risk. High risk part is done first. Because you're not taking the whole thing at once, you can take part by part, and the high risk ones are first. With every increment, operational product is delivered. So every increment, like increase in the development, every stage, the operational product is delivered. You can produce a workable model and give. Issues, challenges, and risks identified from each increment can be utilized or applied to the next increment. So from one to the other, you can apply. Better suited for large and mission critical projects. This is not suited for a small one-man program. This is suitable for large and mission critical projects. Mission critical, like if something goes wrong, if it affects badly, very badly, losses and damages, injuries, all those things concerned, this is for that kind of thing only, this is suitable. During the life cycle, software is produced early, which facilitates customer evaluation and feedback. So here, customer evaluation and feedback is only at this stage, only at the final stage. So if something fundamental is wrong, some mistake has been done in the requirement specification, then what happens? You have to go right back to this place and then start over again. Whereas here in this case, during the life cycle, software is produced early, which facilitates customer evaluation and feedback early. Then there are some drawbacks. They include only large software development projects can benefit because it is hard to break a small software system into further small serviceable modules. So as we saw that the modules they're broken into modules and then they can be done parallelly. Here it's not it's not possible if it's a small one to break it down to smaller, even smaller ones. So this is suitable only for large ones. More resources may be required. So that's another reason why it's not suitable for a small project. More resources, that means more programmers and more computers are required because they're doing parallelly. Design issues might arise because not all requirements are gathered at the beginning of the entire life cycle. So here in this case, you finish the analysis completely. The entire analysis is done before going to design. Whereas in the iterative, you just take just one small part and then do. The analysis is done only of that part. So defining increments may require definition of the complete system. So until you finish the system, you can't do this. Define the increments. What are the stages that are added? Then the third one is rapid application development, R&D model. Straight away, the benefits include the following. Changing requirements can be accommodated. So this method you can in this place. At this place, if there is the user says, okay, we decided we changed our policy. We took a policy decision at yesterday's board meeting, and then we had to change it. So we had to go back then, again restart. But whereas here, changing requirements can be accommodated because they are small sections like iteration, iterative method, but even more quicker than that. That's why it's a rapid application development. Progress can be measured from the beginning. Productivity increases with fewer people in a short time. So you have only few people, but productivity increases in a short time. Reduces development time. So again, the name rapid comes. Reduces development time. Increases reusability of components. So this is the real modular programming thing, like modules. You do in modules and then integrate them. Those modules can be reused in other programs. You don't have to write again. Then increases quick initial reviews occur. Quick initial reviews occur. Reviews, like the customer will tell what it is. Is it good, bad, or what are the mistakes? Encourages customer feedback. So from the very beginning, the customer is involved and he will give the feedback. Integration from very beginning solves a lot of integration issues. Integration means like if supposing now this is one module, this is another, like that there are so many modules, they are tested separately. This one is tested separately. Just an example. Instead of drawing it, I'm just taking this. This is one module. It's tested independently. It can be done. What when all of them put together, there'll be errors. This may not agree with another module. Some parameter passed from here to there is not accepted. One parameter is missing, or various things can happen when you integrate. So encourages integration from very beginning, solves a lot of integration issues. So at the beginning, if you just, imagine like this module start, this is the beginning. This module, this is the beginning. You can check these two, integrate these two, and then see if there's any initial problem. But imagine that this is gone up to this point, and this is gone up to that point, and then integrate. If there's an error, you have to change the whole thing. Changing a big one is difficult than changing a small program. It's understood, no? Then the drawbacks include the following. Only systems that can be modularized can be built using RAD. So modularized, modules, functions, procedures. If you can't break them down into these, you can't do. If it is just one program, you can't use RAD, rapid application development methods. So only so we are big programs which can be modularized. So because of that, the drawback is that you can't use it for small programs. Requires highly skilled developers and designers. So it's rapid and you need highly skilled developers, and designers have to design quickly when the change takes place. So with every new increment, you have to design quickly, and the developers have to develop quickly, the programmers. Suitable for systems that are component-based and scalable. So if there are like components and scalable means like from this version to the other version, and take it up to a higher, larger scale, or break it down to a small one, like that. Components, they are made out of small parts. Requires user involvement throughout the life cycle. That is another drawback, where the user doesn't like to stop his work and come and test this program and give the feedback. So it requires user involvement throughout the life cycle. So that means it's a drawback. Difficult to get the user. Suitable for projects requiring shorter development times. So if you have enough time, then this is not suitable, because this can be expensive, this method. So it's not suitable if you have enough time. This is suitable only for very quick, short-term ones. Then program design using structure charts. So now we saw the three methods. We saw the cycle first, then the three methods, then come to one way of like program design using structure charts. So structure chart is alternative to modular design. Shows interrelations between the modules. These are the modules. Shows the interrelationship. Each box of the structure chart represents a module. So here's a module, here's a module, here's a module. This is the main module. Each level is a refinement of the level above. So this is refined above each level. This level has 3. This level 0 has only 1. Refine means breaking down some more. And then 3 here. If you go down this one, some more down, that's level 2. That's also some more or details, refinement. Each level is refinement of the level above. Shows the interface between modules and the variables, the parameters. Interface is this interface, these, the parameters. The parameters pass between modules, and those are variables generally. And the variables, right? They are called parameters, pass through these modules. Then looking at the keyword structure chart, a graphical representation of the modular structure of a solution. So read this and try to remember. Structure chart is a graphical representation of the modular structure, these modules, structure of a solution. Then the parameter, a value passed between modules. So these are the parameters here, number 1, number 2, number 1, average, pass, like that. Those are the parameters. A value, parameter is a value. Pass between modules, from this module to that module, like that. And the diagram is a structure chart for a module that calculates the average of 2 numbers. So what really happens is, now this is the main program, the averages, broken into three modules. The first module is input numbers. So number one and number two will be input. They are passed. Get the main program. Then going on to calculate average. These two parameters are passed, the values. Then the value is calculated, the average is calculated and passed back to the main program. From there, average is sent to a module to print it. Output average. That's very simple. And here is a task. Here is a task for you to do, but I have done it below. Draw a structure chart for the following module. Input a number of kilometers, output the equivalent number of miles. When you input like say 10 miles, output the equivalent number of miles. No, kilometers, then you have to divide by, you have to find the formula, divide or multiply by so much and give them in miles. Right? But don't go down. Now pause the video. Pause the video and then try to draw this on your own. Looking at this, you saw how this was done. Try to draw it. After drawing, look at this diagram. I have given the answer. So kilometers to miles, then input kilometers, input a number of kilometers, output the equivalent number of miles. So input kilometer, the kilometer is the variable, how many, like 10, 15, 30, 10.5 or whatever it is, goes to the main program. Main program sends it down to the place or the module where it is converted to miles. Then you get the miles back and then send it to output miles, just like this. Very similar. Almost the same, like only the variables are different. Output miles. Here is output average. So you must always try to do these tasks alone, then look at the answers where they are given. Now let's look at one chart, structure chart with using selection. Now here there is no selection in these two structure charts. Let's look at one where there is selection. Selection means if then else. So number guessing game. Generate secret number. Generate the secret number. So a random number is generated and even the programmer doesn't know. So input guess. Also the guess is also. Now to this module, the secret number is not going. Can you see? It's not going. This secret number is generated. The main program gets it. The input guess, main program gets it. Now you use this module to see whether it's right or wrong. So the secret number and the guess both are same. Then are both same. Like guess equals secret number. If it is yes, true, then output congratulations message. If it is false, output a consolation message. Better luck next time or something like that. So a structure chart for a number guessing game with only one guess allowed. There is no repetition. Now we have come to with selection, but no iteration done. Let's do one with iteration. This is the structure chart for pyramid drawing program. We have all done all those things. Pyramid drawing. Then this is the main one, and these are the modules. And here is another module, sub-module. Input max number of symbols. If it is 9 or something, it has to be an odd number. All those things are looked into. We have done it. Then max number of symbols is passed on to this. Initialize values, and these are the ones. Once initializing, they will be passed number of symbols, number of spaces, max number of symbols, and the symbol itself. Which one is a symbol, it may be asterisk or something, all those go. Then from here, this is the symbol assigned for iteration. This arrow. And the condition is given here until number of symbols equals max number of symbols. Max number of symbols here until that is equal to the number of symbols. Number of symbols here. Then you have to stop. So what is being repeated is output spaces first. then output symbols, and here, what is this? Number of symbols, number of spaces. These two are passed on to this, but adjust values for next row. Uh, this is a module where it will adjust values to the for the next one, for the next row when you are printing. So then it starts again from here. We'll check the condition. Is number of symbols equals to max number of symbols? If not, continue. Output spaces. So output the spaces. You remember we did the pyramid printing. Then output symbols on the screen, these number of spaces and the symbol. First time, if it is 9, if the max number of symbols is 9, you remember the spaces will be 4 and the symbols will be 1. The next row, spaces will be 3 and symbols will be also be 3. This is reduced by 1, this is added. 2 added every time. So when that is finished, when this condition is satisfied, only it will stop. Then the whole pyramid is drawn. So here are two subtasks. Amend the structure chart for the number guessing game to include repeated guesses until the player guesses the secret number. The output should include the number of guesses made. Here 15.02, the same thing. How do you do? The requirement is include repeated guesses until the player guesses the secret number. The output should include the number of guesses made. So the main program here is number guessing game, that generate secret number, okay. And this, from that point onwards, it's a loop, these two main branches. Guess secret number. So, sorry, this guess is, the guess is passed. No. Yes. Yeah, that's right. The guess is, the input guess, that is 1. Input guess, the guess is passed. Then secret number also checked. Input, no, sorry, guess secret number, the guess is passed. And input guess, and then increment number of guesses. You have to add 1. You have to add 1, increment is that, add 1 to the number of guesses. So then for the output message, and also the at this point, look at this condition, where this is repeated until guess equals secret number. Until guess equals secret number. So what is done? The guess is passed, the number of guesses passed, secret number is passed, output message. Check these two, guess and the secret number. Are they equal? If it is equal, output congratulations plus and the number of guesses also, because this says the output should include the number of guesses made. So output congratulations plus number of guesses. Num guesses is the variable used to accumulate the number of times, and the plus is the concatenations symbol or sign for the pseudocode. Plus is at is better than that, right, in pseudocode, but this is like structure charts, they have given like that, so it doesn't matter plus, but ampersand or and is a better one. This and the number of cases, and if it is false, output try again, a message like that. Consolation message. Here is 15.03. The next one is that 15.03. Draw a structure chart for the following problem. A user attempts to log on with a user ID. User IDs and passwords are stored in two 1D arrays or lists. The algorithm searches the list of user IDs and looks up the password in the password list. the user is given 3 chances to input the correct password. If the correct password is entered, a suitable message is output. If the third attempt is incorrect, a warning message is output. So have a good look at this. I'll expand this. Yeah. See how are given, because it's too early for you to do alone. I'm showing the answer also. So login, user ID, input the user ID. The user will type the user ID. It will come here. Then start the loop until number of it will do until number of attempts equals 3 or until password is valid. That means you need not input 3 times. If the second time, if it is, or the first time, if it is valid, then you exit this loop only once. But if it is invalid, then you go on for 3 times. Then only you finish. So user ID is sent here to check the user ID. There's a list, no? List of users. The algorithm searches the list of users. So for that, check user ID, it will come here. Then valid is returned. Valid is returned. It's a flag. It's a flag. Flag. This dark, can you see the difference? The round, solid round here, solid circle here, instead of this empty one here, hollow, the empty one. But here is solid, full. That means it's a Boolean value, either true or false only. So if the user valid is user ID is valid, then true will go. User valid ID true. Otherwise, valid ID false will go. Then what happens from this one? Input password. Now, once that is done, you have to input the password and then also increment number of attempts, just like the earlier one. Increment number of attempts. So password is gone to the main one and then send it back here to check valid password. Check password, and here also again Boolean return. Right? And also here there is no room, because of that I put number of attempts should go like this. This arrow there, and then the number of attempts also should go back, because you are incrementing the number of attempts here. Updated number of attempts will go back here. Then valid password will come back, and because the password is sent here, check password. And another module, if it is for the output, if it is valid, output resolution method. False, then number of attempts, if the number of attempts equals 3, then if it is true, output warning message also. If not, continue until this becomes 3. Number of attempts equals 3, or if it is true this way. If the valid password is true this way, or if the number of attempts is 3, or if it is false this way, and then check the number of attempts. And if it is 3, output warning message. So I have to mention a certain thing here. This both side arrows, number of spaces, one circle, and both directions you have opposite directions, the arrow. That means it processes this variable, this parameter is processed inside this module and then returns, updated rather, right? Then Booleans are not there, Boolean flags. Here it's a, oh no, we have not come to this yet. So we are done 15.03. That is this one, 15.03. Then you go to structure charts help programmers to visualize how modules are interrelated and how they interface with each other. How they are interrelated, the modules, and how they interface with each other. The interface is this, no? Yeah. An arrow with a solid round end shows the value transferred is a flag. a Boolean value. So in this case, here, winner found. Generally, winner found, it's a flag, no? This winner found, flag, dark rounded end. Here's another one, winner found. Here, valid, true or false. Here, again, the winner found, same thing. Game finished. Also, solid end, round end, Boolean. Here also, game finished, Boolean, right? Second one, a double-headed arrow shows that the variable value is updated within the module. That is like this player goes there, then gets updated, swapped, and then comes back. So this is the Connect 4 game. You remember Connect 4 game we did. So initialize board, then the board is sent to the main program, and then setup game, that is this player. We set up this player as O or X or whatever it is. The starting one, you have to set up. And then the game finished, you have to say, no, it's false. Game finish is false. So those two are the things that have to be set up. That's done. And then you start the loop. Player makes move. So when player makes move, the player chooses column. Player chooses column. That's how you do. Either there are 7 columns and 6 rows. So player only can select a column. Row is automatically what is available next will be used. So player chooses column, and that time the board is sent to the screen. On the screen, the board will be displayed. Otherwise, the user cannot select the column. That's displayed, and then the player chooses column. What happened? Check column number valid. So the board is sent here. Then the column number selected is sent here. Then you check and return the value whether it's valid or not. When can it be? When can it be invalid? Like if you enter 0 or if you enter 8 for the column, you can enter only 1 to 7 in one of them. Then if the thing is valid, comes back, then column valid number is returned, then column number is sent again here. Board is also sent to get the row. Find free row. Where do you place the token? At the bottom, that is row 6, or up 5, 4, 3, whatever, right? So, sorry, not row 6, row 1 at the bottom. Now, in this case, we are doing the opposite way. Normally, a list or the array, the top one is a row 1. Then row 2, row 3, like that. And the columns, vertically, it goes column 1, column 2, column 3. But rows, in this case, in this game, you don't start at the top. No? Row 0, you can't put a token there at the beginning. It will drop to the bottom. So bottom is 6. Sorry, again, it's confused. That's right. That's correct. What I said initially was correct. Bottom is 6. So you start from 6, the board. Usually anything is normally you start from the top. But here you start from the bottom. So check whether the row is valid. Row number. Find free row. When the column is valid, they say third column, where to place the token. Where to place the token is not entered by the user or the player. It's decided by the program. So this is how the program checks what is the next available row. So that row number will be returned here. Then this player is returned. This player is set 0. The board comes here, and then output board. That is because the board has to be updated. Board is updated with every move. Every move, the board is updated, and then output board is here. With every move, the board should change on the screen. Then the next one is you send the board again to see whether the game is finished. Every time the user or the player places a token. It can be the last move. By how? It's a winner. That's his last one to connect 4 in a row or a column, vertically or horizontal, or the game is finished. That's the last slot available on the board. The next player cannot find a slot to put the token. That means the board is full. So for that you check. How do you check whether the game is finished? Check if player has won. First you check whether the player has won. That is the horizontal line. Check horizontal line by sending the board, sending the row number, column number, then returns a Boolean figure whether the winner is found. How do you check whether the winner is found? Supposing here, the column is, let's say 4. The column input is 4. Right? And you check whether this, and that are 4. Or whether this, on this column, on this row only, where this column, where the last one is placed here, then you check whether these 4 are the same, whether X or O. Now in this case, these are 3 O's and 1 X, the last token. Or whether these 4 are the same, or these 4, or these 4 are the same. If it is the same, now in this case it's the same, the winner found. So is winner found? Yes, it will go back here. If not, check whether now this is horizontal we checked. We checked horizontal. If a winner is not found, we have to check this way. If it's a column, this column, the last column only, we have to check, and this one, because previously all this was done. Every time token is placed, these two horizontal check and the vertical check is done to see whether the winner is found. So here what happens? If the winner is found like that, otherwise the horizontal way, otherwise you check the vertical line. Similar, same thing. Column number, row number, and the board is sent. It will check. It will check whether this way you have 4. Either these 4 or these 4 or these 4. Right? You don't have to check the others because there is no, that if it is here, now even in this case, this is only 3 here. You can't have a 4. So only up to this point, if you check, that's enough. That you will see when we are doing the coding. Then either this way or that way, if the winner is found, check if we have plot. The winner found will go back, and then is the winner found? If it is yes, and if it is yes, if it is yes, then game finish is returned here. Game finish return, and this player. No, if nothing will happen beyond that, because this will happen while game not finished. But here game is finished, no? Because if a winner is found, then the game is finished. If not, you check for, if it is false, check for full board. Is the board full? Right? That means you can't, all these are full. The last token to put is here. All the others are full. In that case, the board is full. So then also the game is finished. Check for full board. Board is sent here, then game finished. The Boolean value is returned. So if the game is finished, then that's it. Otherwise, what will happen? If the game is not finished, if this is false, the value returned here is false, what happens? Then you continue. This player is sent. If this player is O, starting with O, if O will come here and it will be made X. If it is O, it will be made X. If it is X, it will be made O. Then returns and starts again. Starts again from here. Player makes move. Now the other player, the opponent will make a move, then the cycle goes on. Deriving pseudocode from a structure chart. Now, how are you going to write the pseudocode? Using local variables and parameters. Local variables. When you declare anything within these, they become local. They are not available. What you initialize values here, what you give a value to the parameter or the variable here is not available there. If you say a equals 10, if you say here a equals a plus 1, and there is no other a in this module, it will give an error because this is not available there unless you specifically say it's global. Otherwise, it's local. So using local variables and parameters. Modules are then self-contained. Modules are then self-contained. And any changes to variables do not have accidental effects on a variable value elsewhere. So that is why it is like that. You have it here. And the values here are not affected by any other module by accident. For safety, it's like that. So here is the structure chart for pyramid drawing program. So let's how do you do the pseudocode? Module pyramid, that's the main program. That's the main program, main module, pyramid. Here is the structure chart, like not structure chart. This is pseudocode because call is the way to call a procedure in pseudocode. So call set values. In our main thing, set values is here initialize values, set values, right? So you need the number of symbols, all the values here. Can you see number of symbols, number of spaces, symbol, max number of symbols, all passed to this call set value. Then what happens? It won't go here. This pseudocode, when you design, you must know that when you have a thing like this, it will not, the control will not go there. Instead, where will it go? It will go there. We have done this before. In chapter 14, I have described drawing lines and all that like this, where it will go. But briefly, I will remind you of that. This set value will go here, looking for instructions. Here, there are no instructions. Here, this is just a case of calling this procedure. And since there are no instructions, it will look for this, find it, and then carry out the instruction. The same number of parameters, same parameters are sent. The input symbol, okay? It's not given in structure chart, but input will do it like that. Otherwise, if it's not there in the structure chart, what does it mean? The programmer sets it as an asterisk or ampersand or a, letter A or anything, hash sign. But here, I'm just making a small change because we should be able to change anything, anytime. If we have the knowledge, we can change. Otherwise, we don't know how to change. So here we can change it and with a meaning. Input symbol. Then call input max number of symbols. Because here you have to get the max number of symbols. From this point, you have to call another one. So here you stop there and then instead of going to number of spaces, you go look for input max number of symbols and you find it here. And then you do that. No need to go through details because we have already done this 2-3 times. Then when you finish this, what happens? When you finish this, where it will go where you came from. Where we came from, this place here. Call this. So then you do this. After that only you do this. After doing this thing, after carrying out this procedure, you come here and do this. Number of spaces equals. And here again, max number of symbols is another function. Where is that? There'll be somewhere else. Here the input max number of symbols. So max number of symbols. Then that will have the function. This is a function. Remember, I'm just reminding you. You have already done. There's no word called call here. The word call is not here, but assignment. The value returned from this is assigned, isn't it? It's assigned to this. And then number of symbols equals 1. So when you finish that, from where did we come here? For the brown thing, so the yellow one. Now we have finished the yellow one. So go back here. Now this is done. This is done. Now we go to all output spaces. So output spaces is here. Then you do that, come back here. Output symbols, I have color coded, it's easy. Output symbols, you do that. Then adjust values for next rows. And that's it. You repeat. All those things, adjust values for repeat until number of symbols greater than max number of symbols. So until you reach the bottom of the pyramid. Goes on. This is the main program. Modular programming is like these are broken into small programs. This can be tested separate. This can be tested separate. And then you put them together. That's integration. Note that a structure chart does not give details about how parameters are passed, whether it's by reference or by value. You will be doing that by reference and by value. That's a slight difference. You will know that later. Then here is a task. Write pseudocode to implement the structure chart form from figure 15.03. There's a mistake here, not 12. It's 15. For the average of two numbers. Write pseudocode to implement the structure chart from figure 15.04 for the number guessing game. And amend the pseudocode from worked example 13.05 to implement the interface shown in the structure chart from figure 15.06. Let's look at the answers for these. Again, I'm telling you, it's better pause the video now and do these three on your own. Doesn't matter making mistakes. It's very important that you attempt. When you make the mistakes and then see the correct one only, you will remember it. So let's see the answers. Yeah. The first one. First one is write pseudocode to implement the structure chart from figure 15.03. This is 15.03 structure chart for a module that calculates the average of two numbers. For the average of two numbers. So looking at this, you can say the call input numbers. This one, call input numbers, then average, then this one, average. It's a function returning a value, see, returning a value. So because of that, you don't use the word call. Say average equals calculate average. This is the name of a function. And you pass on these two values, number 1 and number 2. You have to say as integers, both. And the returns integer. The value that is returned is an integer. That you have to mention this. So calculate average will come here. Then do it. And input numbers for the first one, call input numbers, will go looking for this. When it finds here, do that. Output enter number 1, that is the number 1 and number 2. Input number 1, then input number 2. Then calculate average, this one, this module. Average equals number 1 plus number 2 divided by 2. And return average. When that comes here, return average. Then the output average. This, the last one, output average. Also is a module, so that we find it here. Output average equals and is the concatenation for in pseudocode, and average, the calculated average here. End procedure, that's it. That's the answer for that. Then 2 is write pseudocode to implement the structure chart from for the number guessing game. Now we already know that number guessing game. So secret number is integer, you are declaring it. Secret number equals random. Output, enter your guess. Right? So if the secret number equals guess, you input guess. If it is equal to guess, then output congrats, else output better luck next time. So that is, I have not taken the 15 thing, but it's there. 15.04. Let's see whether it's in this. Not in this. Yes, 15.04 is this. So input, generate the number, input the guess, and now if it is equal, output congratulations. Otherwise, consolation message. And the third one, amend the pseudocode from 13.05 to implement the interface shown in the structure chart from figure 15.06. Yeah, the third one, third question is here. This is the structure chart. No, this is the second one. Yeah, third one, you better do it. In 0.06 is this, yeah, the third one. You better do that, and then now you have enough knowledge to check it yourself. If you have any difficulty, you can write to me and ask, or post it on the forum for the other students to answer. Amend the, sorry, now program design using state transition diagrams. So another, like the structure chart, there's another way of doing it. There's a thing called finite state machine, FSM. An FSM has a start state. An input to the FSM produces a transformation from one state to another. So change of state, transition. Here are the keywords again defined. Finite state machine, a machine that consists of a fixed set of possible states with a set of inputs that change the state and a set of possible outputs. State transition table is a table that gives information about the states of an FSM. So this is a state transition table. The current state is S1. When the current state is S1, you input A, there is no change. It remains S1. That is, if you look at this diagram, the S1 is the current state, and input of A doesn't do any change, stays in the same state. But input of B, when the current state is S1, input of B here will change it to S2. This is S2. This is the S2 state. This is the current state now. And if you're taking S2 as the current state and input of A here, input of A will change it back to S1. That's why S1 is here. And if you input B, no change. It will remain in S2. All right. When you put an arrow coming back here, it says no change. Easy. If an input causes an output, this is shown by a vertical bar. That is this vertical bar here. For example, if the current state is S1, this one, and input of B produces output C. Here is the input B on the left side of the vertical bar. Right side is the output. It's very easy. And transforms the FSM to state S2. Not only the output of C, but it transforms it to S2 also. So when it is S1, input of A, what will happen? Input A will not produce an output of E and remain in the same state, will not affect any change. Input of B when in S2, when in state 2, input of B will produce an output of F, but no change in the state. Also, again, if you input A when you are in S2, will change it to S1, back to S1 as well as produce an output of D. Actually, it's easy, very easy. Let's do a worked example. Creating a state transition diagram for an intruder detection system. A program is required that simulates the behavior of an intruder detection system, a burglar alarm. Description of the system. The system has a battery power supply. The system is activated when the start button is pressed. Pressing the start button when the system is active has no effect. To deactivate the system, the operator must enter a PIN. So only the user or the operator can deactivate it. The burglar cannot, because the PIN is with the owner. The system goes into alert mode when a sensor is activated. So if a sensor detects a movement, then it goes to alert mode. The system will stay in alert mode for 2 minutes. Why? Because if it is by accident, if the owner walks out of the room for something, then he can deactivate. If it is not, if the system has not been deactivated within 2 minutes, an alarm bell will ring. So that is how the alarm system will go. So let's look at the table, the state transition table. Current state, system inactive. Event is press start button. What happens? Next state, system becomes active. Here, press button, press start button. The system inactive, from here to it will become system active. Then when the system is active, that is here, enter the PIN. Enter the PIN here. System will become inactive. So that means, like by accident, the owner has moved, and if he enters the PIN, it will become inactive. Then when the system is active, activate sensor, some movement. Activate sensor, that is this sensor activated. It will change the state to alert mode. Right? When here you press the button, nothing happens. Here, system active, press start button. System active, still nothing happens. Then alert mode, while you are in the alert mode here, 2 minutes pass, alarm bell ring. So 2 minutes pass, we'll change it to alarm bell rings. Alert mode, press the button, no change. Still in the alert mode. Sorry, press here, the press button. In the alert mode, if you press start button, it will be there still. Then alarm bell ringing. Once this is happening, enter the PIN, system inactive. Enter the PIN, it becomes inactive. And press start button, alarm bell ringing. So at that time, if you press the button, no change, nothing will happen. So that is the system. State transition diagram for intruder detection system. Here is another worked example, creating a state transition diagram for a two's complement FSM. I hope you remember the two's complement form we did in chapter 1. A finite state machine has been designed that will take as input a positive binary integer, 1 bit at a time, starting with the least significant bit. You know where the least significant bit is, on the right side. The FSM converts the binary integer into two's complement negative equivalent. The method to be used is as follows. Output the bits input up to and including the first one. This is the shortcut method, not the two-stage one's complement and then adding one, not that method. This is the shortcut straight away. So starting with the least, the FSM converts the binary integer into two's complement negative. Sorry, output the bits input up to and including the first one. So let's see if there is a number, right? The worked example, yeah, 15.02. Imagine that it's a number. Just to remind you, refresh your memory about the shortcut to the two's complement. 1, 0, 0, 1, 0. If this is the number, how you do is, right? You do the normal way. You do the normal way, one's complement and add 1. But I'm doing the shortcut where the program, where the question word example is using. So copy up from right side up to the first one, that is this one, no? This and 0. Then the rest is inverted. Rest is inverted. That means 0, 1, 1. 0 for this 1, 1 for this 0, 1 for this 0, and this. This is the way. So how does it happen? Well, I have to say that it's a shortcut method. All right. So then let's go to this and output the bits input up to and including the first one. So there, the current state, this information is represented in the state transition table shown in table 15.03. Output the bits input up to and including the first one. Let's take that as the example. Yeah, if this is the input. Okay, I have done the same thing here. We'll take a short one. This is the 1, 0, 0, 1, 0. The same number I have taken. And output, let's see how this happens. S1, current state is S1, input bit, output the bits input up to and including the first one. So that means if it is 0, then the output is 0. That is start at the start, this is the diagram. Start the state here. If it is 0, no change of state. Output 0. Input 0, output 0. Right? So in this our case, this is our input. So if we have what do I do here? 0. Output is 0. Output is 0. Input is 0. Output is 0. Why? Here, this is. And no change of state. So next one. 1. 1. Output of input of 1 will output 1. So 1 here. Right? 1 here. And what happens? It changes state to S2. Now we are in S2. S2. And the next number? Input is 0. So why do I in S2? Input of 0 will produce a 1. That is the inversion. So here it's 1. Here also it's 1. Okay. And the 1 will produce a 0. So this should be the answer, right? This should be the answer, 2's complement. All right. So we got it, no, here. Earlier we did that same method, and here is the answer here. Right? If you make it the The normal method is 1 0 0 1 0. The inversion. First state invert 0 1 1 0 1. That is the ones complement. Then you add 1. No? So 1 plus 1 is 1 0. 0 is there. Then 1 is carried. That 1 and this 1 is 1 plus, sorry, 1 plus 1 is 1 0. Then 1 is carried. That 1 comes here. Then the others same. Means 0 1 1. So when you add 1 to 1 complement, this is 2's complement. Right? Same. This is one method. This is the shortcut method, and we are using the shortcut method for this program. So that is how this changes. This is the inversion type. Here, up to the first one, you put all the zeros. Then when the first one comes, it changes the state where the others will be inverted. The output is inversion. This is the output is the same. After the first one, output is 1. Then task 15.05. Write a program that simulates the intruder detection system in worked example 15.01. So that is definitely for you. Look at this and do the pseudocode, right? Burglar alarm. Then we have come to types of error. So now they have finished all the development and all that. The types of error, what are the types of errors that can happen? Why errors occur and how to find them? The program has made a coding mistake. One reason, the program has made a coding mistake. Obviously, there's an error. The requirement specification was not drawn up correctly. As I told you at the beginning, the requirement specification is very important. If it was not drawn up correctly, then there could be an error in the program. The software designer has made a design error. Yeah, that's obvious. The user interface is poorly designed and the user makes mistakes. That means interface is what? Interface is what appears on the screen for the user to enter and see the instructions, enter data and all that. If that is not very clear, very user-friendly, the user can make mistakes. Therefore, the program can make an error. Then the computer hardware experiences failures. That, of course, you can't help with the program, but that also is a type of error. The testing software before it is released for general use is essential. So you have to test it before releasing it for general use. Finding syntax errors is easy. Why? The compiler or the interpreter will find them for you because it will definitely stop working and then say there's an error. So syntax error, the definition, an error in which a program statement does not follow the rules of the language. When a program compiles successfully, you know there will be no syntax errors remaining. This is not the case with interpreted programs. Only statements that are about to be executed will be syntax checked. So when you test, you will find errors. Finding, as I told you earlier, finding syntax errors is easy. The compiler interpreter will find them. But there are things that you must consider. I'll tell you in a little while. Let's go through these. As I said, syntax error, an error in which program statement does not follow the rules of the language. Then when a program compiles successfully, you know there will be no syntax errors remaining because either the compiler or the interpreter will point it out and then stop. This is not the case with interpreted programs. See, the compiler will stop because, and it will not produce the executable program. But what happens with the interpreted? only statements that are about to be executed will be syntax checked. So let's look at, okay, let's finish these two also and then look at the three types of error. Now the logic error, an error in the logic of the solution that causes it not to behave as intended. So there is no syntax error. The program works well, but it will not give the required or the desired answer, the result. That is logic error. The runtime error will be there is no logic error, there is no syntax error, but an error that causes program execution to crash or freeze. So let's take the syntax error first. No, let's take the logic error first because that's easier. Now I'll take the Python program logical error. Here I have a program done in Python, which is input the mark, right? Enter mark. Then if mark is greater than 50, print pass. If it is less than 50, print fail. So it doesn't look that there is any problem. Let's run it and see. Enter mark, let's say 80, it says passed. Let's run this again and enter 40. Okay, fail. So that's perfect, no? But if I input 50, what happens? Nothing, no result. Why? Because this is greater than 50 and this is less than 50. For 50, we have not given any grade. So that's a logical error. There's absolutely no syntax problem. It's a logical error. The program works. And then the next one is, let's take the syntax error. Here is a program. Make this a little bit shorter here, easy. This is if m is greater than 50, print pass, else print fail. So let's run this and see. Enter mark, say 80, passed. Okay, no problem. I'll try 50 also then. 50. Then what happens? Else, that means this is, if it is greater than 50, only this is interpreted. Only this is interpreted. This is not interpreted, this one, else. Because only one of them, no? If it is true, this will happen. This will not be interpreted. It will be interpreted only if I put 50 or less than 50. Right? Say 40. Also same. Why? Because there is a mistake here. That's a syntax error, no? The name print is not defined. Do you mean it's print? See, there is a problem here. But that will take place only if this is less than 50 or less or equal to 50. So, but the compiler, if it is compiled, it will give this also. Compiler will go through the entire program, whereas interpreter will interpret and execute only the ones that are necessary. Now, this is not necessary if it is 50 or more, 51 or more, no? If it is 51 or more, this part is not necessary for this program. Only this is necessary. But if you enter 50 or anything less, then this part is necessary and not that part. At that point, when it interprets only, it will find an error. So it may be that maybe even after 1 year, this will happen. So that is why you have to be careful. Now this runtime error. Runtime error. Famous one is division by 0. Right? It's called division by 0. Supposing now there is a loop going on, and then B divided by C. So there is a range, there is a loop going on in times, and C being divided, C is being subtracted by 1 every time, every iteration. 1 is deducted from C, and then C is 4 at the moment. So the fourth time, or third time, this is at the beginning, it becomes 3, no? After the third time, it will be 0, and then be 20 divided by 0. When you print, it will give an error. The first 2-3 times, no error. Let's try it. See, first time, C is 3 here at this point. B is 20. So it will be A equals 20 divided by 3. So it's 6 point something, all the sixes. Next time, C becomes 2. And then 20 divided by 2 is 10. Third time, C becomes 1. And 20 divided by 1, 20. Third time, or the fourth time, or C becomes 0. Then B 20 divided by 0, and the problem becomes there. And this says division by 0. So these are the 3 types, right? Then testing methods. What are the testing methods? Stop testing. Test before you have implemented all the facilities. You can write a stub for each procedure. Stub is a short one, short thing. Black box testing. As part of thorough testing, a program should also be tested by other people who do not see the program code and don't know how the solution was coded. That is, you don't see the inside or the program, the coding. That's why it's called black box. Look at the program specification to see what the program is meant to do. Then device test data and work out expected result. So they only just look at the requirement specification, program specification, what should it do? Then test it and see whether it does what it's supposed to do. Then test data is carefully chosen values that will test a program. Black box testing, comparing expected results with actual results when a program is run. That's what we saw here. Stub testing is before doing the whole module, just do a small thing and then see whether it reaches the correct place, whether it accesses, whether it passes the parameters before completing the module. That's stub. Stub is a short. Then you have the white box testing opposed to black box. Choose suitable test data that checks every path through the code. Right? That means you go through this and then see every path and then see whether it's correct. Let's have a look. White box testing of pseudocode. White box, because you can see that it has to be a programmer, because who knows this programming. Otherwise, you can't do that. But this black box is the layman can do. Those who don't know about the program. But here you have to see the program. That's why white box testing. And you have this input number 1, 2, and 3, and then find the largest one. It's written here, each line, input number 1. This is one set of test data. 15, 12, and 8, we have to find which one is larger. This is test 2, same numbers, but in different order. All 4 tests are like that. So let's put input number 1, 15, 12, 8. Then if number 1 is greater than number 2, that's the first one. After the input, is number 1 greater than number 2? So here it's yes, no? 15 is greater than 12. So it's true. The answer here is true, because this is always either true or false, the if statement. Then what happens? If output, and this is also, number 1 is greater than number 3 also, no? Because 15 is greater than 8 also. That is also true, those 2 conditions. So in that case, output, number 1, 15. That's all. Nothing else will do. Nothing else will happen. That's why this is all blacked out. Nothing else will happen. Only this, one of these will happen only. So output 15. And the next one is the different order. If number 1 is greater than number 3, sorry, this one, number 1 greater than number 2, true. 12 is greater than 8. But 1 is greater than 3? No. 8 is not, 12 is not greater than 15. So that's false. Then what happens? This will not happen. Then it comes here. Else output number 3. So number 3 is this 15. Same way, here also you go through number 2, and then you find that number 2 is greater than number 3. And this number 1 is not greater than number 2. In that case, number 2 is output number 2, that will be 15. And in this case, output number 3 is 15. So this is not a trace table like a trace table, but this is testing and checking the answers, whether the results, whether that is correct. Now here is a dry running, it's a trace table. Dry running an algorithm using a trace table, or they say code walkthrough also. Dry run is walkthrough, the process of checking the execution of an algorithm or program by recording variable values in a trace table. This is the pseudocode and this is the trace table, and then see how it is done. Secret number, let's say 34. I is given. Secret number equals 34. So we can store it here, secret number. Then the guess, those guesses are not given. These are the numbers that will be input. So guess, first time you input 5, the number of guesses equals 1 here. Number of guesses 1. That's a variable we have to monitor. Then guess is greater than secret now. Is guess greater than secret number? That is 5. It's a 5. This greater than 34? No. So that's false here. False here. And then the appropriate message. Guess a smaller number. Guess a larger number because 5 is smaller than 34. Then 55, the opposite happens. And also number of guesses, we have to add 1. Yeah, it's here. After every guess is input, number of guesses equals number of guesses plus 1. So this is increased 1 by 1. Then this is true. 55 is greater than, is guess greater than secret number. 55 is greater than 34. So it's true. And then you have to input a smaller, guess a smaller number. It goes on like that, and the counting goes how many times the guess is done until this becomes equal 34. That is, if guess equals secret number, that is the very first one, only these things happen. So guess, until guess is secret number, until guess equals secret number. So here, when the guess is, when you input, input is here now. Input is here and there, those two, right? So if the guess is equal, then what happens? Here it exits. Repeat, until guess is secret number. Guess equals secret number. So at that point, you exit, and then what happens? Number of guesses equals 7. Then the message is output you took number of guesses, so many, 7 guesses. This is a variable, the value is 7, and this is a constant, guesses. This is also constant. So if the guess equals secret number, this is the output. So that is the last part. And then you exit. That's it. Finish. Nothing of these will happen. If this happens, this will not happen. If this happens, if this happens, this will not happen. If this happens, that will not happen. So only one of them will happen. So that is easy. Then this one, design a trace table for the following algorithm. Function convert from hex. Returns integer declare. So this is, you have to write like this. And actually this, you don't have to do anything. You have to only run the function call convert from hex A5. A5 is the number that you have to convert by completing the trace table. Let's take this task 15.06. Design a trace table for the following algorithm. Function, this is a function to convert a hex string to denary. And I run the function call convert from hex. Convert from X. This is the function name A5. A5 is the parameter that is being sent a string as a string A5 and returns integer A5 by completing the trace table. So let's do that. Yeah. So in the trace table, we have X string is A5. It's given in the question. Then I, we have I as integer because we are starting from for I equals 1 to X length. What is the X length? X length equals length of X string. X string is coming from here. That's A5. So X length equals length of A5 is 2. So this in effect is for I equals 1 to 2. Hex digit. Hex digit declared as char character, just one character. So hex digit equals hex string I. I is the index. Hex string is A5 and this means first time it's A. So case of hex digit. Remember the case and case statements. So if it is A, then hex value is 10. So in our case, it's the very first one is A. So no need of this. We have it here now. The whole thing. Yeah. So A5, hex string is A5. I is one. Before that value so far, we have declared value so far 0. Here, value so far is 0. Then hex length equals 2 of this A5. Hex length becomes 2. And for I equals 1 to 2. So first time it's I is 1 and value so far. How do you check the value so far? If it is A, then hex value is 10. B, C, D, E, F, you go like that up to 15. So it's 10 and hex value so far is 10 because hex digit is A. Hex value is transferred here. How it is done? Value, because this is done, n case afterwards value so far, that is this one, equals value so far into 16, that is 0 into 16 is 0 plus hex value. Hex value is 10. So we write 10 here, value so far, and go back. Next I is I becomes 2. When I becomes 2, the second digit, second character is 5, A5, 5. So case of it doesn't happen because it's not A to F, it's 5. So then what happens? Hex value equals, otherwise is that, otherwise if not this, otherwise string to int of hex digit. Right? The 5 becomes, now here it's this, no? Like a character. So the hex value becomes an integer. It's an integer, 5. This is a character. It's a character and this is 5 as integer. Then what happens? Value now after this value so far equals, that is this 10, which is here now, equals value so far into 16. That means 10 into 16. 10 into 16, 160 plus x value. X value is 5 numeric, and it's 165. And the return value so far is 165. So if you just check A5, convert A5 to denary, it will be 165. Well, A is 16 into 10, 5 is 1 into 5. Right? And then what? This one. Then we go to like integration testing. They are giving a little later about these things. Actually, they should have gone up. Yeah, at this place. After this only, it should come. So, what is this? Integration testing, individually tested modules are joined into one program and tested to ensure the modules interact correctly. And alpha testing, testing of software in-house by dedicated testers, acceptance testing by customers before sign-off. Before they accept and make the payment, they have to accept. Beta testing is testing of software by a limited number of chosen users before general release. Test strategy, test plans, and test data. In the first instance, an outline plan is designed. For example, flow of control. How does the user get appropriate choices, and does the chosen option go to the correct module? That kind of testing you have to test. The validation of input. When you input, you have to check, has all data been entered into the system correctly? Do loops and decisions perform correctly? Is data saved into the correct files? Does the system produce the correct results? All those things. This outline test plan needs to be made into a detailed test plan. So the type of test data is normal, abnormal, and boundary, as I told you earlier. Typical data values that are valid, then this is the error, should not, these are erroneous, should not accept. And this one, data values that are at a boundary or an extreme end of the range of normal data. Test data should include values just within the boundary, that is valid data, and just outside the boundary, that is invalid data. Then worked example 15.06, designing test data. Look at the pyramid problem. This is a simple program, but we can use it to illustrate how to choose test data. There are just two user inputs, the number of symbols that make up the base and the symbol that is to be used to construct the pyramid. Let's consider just the test data for the number of symbols. So here you can say normal, it's 7, because 7 is an odd integer, should be accepted. Then abnormal, -7, should not be accepted because it's a negative number. And 8 should be rejected. Why? That's an even integer. With even numbers, you can't have a pyramid. You can't have a pyramid. It has to be an odd number at the base. 7.5 is a real number. That also you can't. Then this non-numeric input for the number of mm, uh, for the number of what you call the symbols, you can't enter a character. This also should be checked. Then boundary extreme, 1, what is the boundary value? The smallest possible pyramid is a single symbol. So the value 1 is just within the boundary. So it should be accepted. 0, no. There can't be a pyramid without any symbols. Right? 79, the output would not look like a pyramid if there were a wraparound. So the program really should check how many symbols fit onto the line and allow the user to input a number of number greater than this. If the number of characters across the screen is 80, like normally you get 80 characters. Standard is 80 characters across the screen. So if that happens, then 79 would be just within the boundary, but 81 would be outside the boundary. So what happens is the base will go like that, and then if it is more than 80, it will return onto the next line. So that will not be nice. So this is how you must check, prepare test data. Task 15.07, look at the program you wrote in chapter 14. Design test data for the number guessing game. So this also you should be able to do, like preparing test data to test the program. Design test data for the Connect 4 game. That also should be able to do. Then how to prevent errors? Tried and tested design techniques such as structured programming or object-oriented design. That way you can, start object-oriented and all that. There are methods of security, safety methods, and using the structured programming or object-oriented, you can prevent errors. Conventions such as identifier tables. We have done this, data structures and standard algorithms, tried and tested modules or objects from program libraries. Instead of writing your own module, look for a already present, already available program modules in the libraries. Corrective maintenance. Work required when a program is not working correctly due to either logic error or a runtime error. You have to do the maintenance, that's correcting an error. Sometimes program errors don't become apparent for a long time because part of the program is not used after often, or because the data on an occasion includes extreme values. So we discussed about that. I did a demonstration on a Python program. Earlier corrective maintenance may also introduce other errors. So when you do a one correction, there can be other errors appearing. So you have to look into those also. So corrective maintenance in effect is correcting identified errors. When a problem is reported, the programmer uses program debugging software or a trace table to solve it. So here is another task. Design a trace table for the following algorithm. Input binary string length equal length. So similar one, binary, this time binary. Run the algorithm using 101 as the input. Complete the trace table. The result should be 5. Can you find the error in the code and correct it? So task 15.08. So shall we try that? Okay, I'll show you that also, so that I'm making things easy for you, but you have to do on your own. Change the size of this and keep both side by side. So input binary string here. We are given 101 as the input. So we have to take it as binary string is 101. And input string length equals length of binary string. So string length equals 3. Length is 3. For I equals 1 to string length. So that is 1 to 3. I 1 to 3. Bit equals binary string I. Bit equals binary string I means 1. So first character of this 1. So that becomes 1 here. Bit value equals integer value of bit. So converted into integer is 1. And bit value equals integer value. Bit value is here, bit value, and bit value is integer. Yeah, that we did. But now the denary value, the last column equals denary value plus 2. So at the moment it's 0, 0 plus 2 plus bit value plus 1, this one. So it's 3. Then it returns with 2. Second character is 2. Second character is 0. And the bit value is 0. So the answer is 3 now here. Denary value equals denary value plus 2 plus bit value. This is 3 now. So 3 plus 2 plus 0. This time is 0, no? Plus 2 plus 0. Then it becomes 5. Then the third time, 1. Digit is 1 and this is 1. So 5 plus 2 plus 1 equals 8. Dry run the algorithm 0. Yeah, that we did. Then this is the answer for 1 and 2. 2 is dry run the algorithm using 1 as it would complete the trace table. That one. The third one is the result should be 5. See, did you realize 101 in binary is 5, but we are getting an answer of 8. Can you find the error in the code and correct it? So this is a very good one for you. So how are you going to correct this? This is my suggestion. There can be others. Dictionary value, this one should be dictionary value equal dictionary value plus bit value into 2 to the power I. 2 to the power I. So dictionary value, when you do this calculation, you will find it's coming like this. 0 plus 1 into 2 to the power 0 equals 1. And this 1 plus 0 is 1. And this 1 plus 1 into 2 to the power 2 is 4 and 5. So now the answer is correct. Then adaptive maintenance. We did corrective maintenance if there's an error. Adaptive maintenance is action of making amendments to a program to enhance functionality or in response to specification changes. Means either improve the program is working perfectly, but you find that okay, how about doing this? We can still improve some, or else change. There is a change, like say what say there's a change in the policy. I told you that we have changed the policy, or say even the VAT is changed, no value added tax, or something else is changed, EPF or whatever it is. Then you have to when the government comes and does some changes, new government or the management decides to do something else. In that case, we have to change it, even though the program is working correctly, but the results may be different because you are now with adapted the new change. That is what is called adaptive maintenance. So Connect 4 game allows two players, the O and X, to play against each other. There's no problem. An amended version would be for one player to be the computer. See, that's adaptive maintenance. There is no error. And still, the third one is perfective maintenance. The program runs satisfactorily. No problem. No need to adapt also. However, there is still room for improvement. For example, the program may run faster if the file handling is changed from sequential access to direct access. So somehow you can change something, right? Perfective maintenance is modifying a program to improve performance or make. So here is a task, design the algorithm to simulate the computer playing the part of player X in Connect 4. That is also a good exercise for you if you can do it. And then finally, this, analyze the pseudocode below and make amendments to enhance maintainability. Function, get positive number, declare and put in the positive number, input n, function, get positive number. But what are the things that you can do here? Right? One is that you can leave a space. This is analyze enhance maintainability. Like giving, like here it says main program, like that you can give comments here, comments, and leave a blank line between this and that, no? To separate them. And the indentation, of course, is okay. Indentation is correct. That is also one thing that you must consider. So those are the ones. Maintainability. That means if somebody else has joined the firm, you have left and somebody else joins the firm and then try to do, it should have enough details like with comments and all that. So that is the end of the chapter. So hope you will do this. You can go through the video again and again and find out what you have not absorbed the first time. Second time you can do, third time and all. So good luck. Now this is the end of the part 1, AS level, paper 2. And so good luck with your exam.